Howdy there, Internet students. Mr. Urmson again. Today we're going to do lesson 6.3b, patterns and linear functions. Basically, a function is an equation, but it can be, you can use a graph to represent a function or a table or just words, just like you could with equations. We're going to find out that it's actually a specific kind of relationship between two variables. Okay? Um, and we're going to learn how to represent something that is a function using notation. All right? So you may have heard this definition before, but may have forgot. A function is a relationship that pairs each input value with um, exactly one output value. All right? So, and sometimes we use this diagram that looks like this. And so what we're doing is pairing each input with the output. And if you see that any input value has more than one output value, then it's not a function. So see if you can find the one that's not a function. So you should have got the middle one. And the reason it's not a function is because you should notice that that the number 1 is actually paired with two output values. It goes with 1 and negative 1. Okay, so does the number 4. But in the other two diagrams, each input value only goes to one output value, and you can tell because there's only one arrow from each input value. Okay, this is again is another review. The input is called the independent variable, and the function's going to do something to that independent variable, and then we're going to get an output, which we call the dependent variable. So the function can be a rule, like maybe it's a doubling rule. So we put in some independent variable like 8, it doubles, and out comes the number 16. So the output 16 depends on what we use for the input, 8. All right? So read these here and write I if the first value is independent of the second value, D if the first value is dependent on the second value. All right, here's what I got for that. The growth of a plant depends on the light received. So the growth is dependent. The speed of a swimmer is independent of the depth of the pool. You can swim just as fast in, unless the pool is only like an inch deep, then it gets a little harder. The number of books a shelf holds depends on the length of the shelf. All right, so we're going to start by looking at these figures, figure 1, figure 2, figure 3. And whenever you have something like this, you could also make a table with x and y values. X would be the figure number. And we're going to look for a relationship and see if we can think of a nice way to represent this. Now, one way to do that is to look at the numbers. So in figure 1, we need 5 tiles to create that. In figure 2, we need 9 tiles. In figure 3, you need 13 tiles. Now, maybe you noticed something when you were doing that that can help you represent this. Okay, one thing that I noticed is that that you actually start with 1 in the middle, and then 4 are added on each time. So I'm thinking that one way we could represent this is the number of tiles is y, is 4 times whatever figure we're on, and plus, if we're on figure 1 and we multiply 1 times 4, we still have to add that 1 in the middle to it. So 4 times x plus 1, that would be a linear function. Okay? If you have a linear function, one way to represent it would be with a graph. Okay? You can also use an equation to represent a function, or a table, or words. Okay? Now, if we're going to call it a function, that means there can only be one output value for each input value. Generally, that's true for pretty much always true for linear functions. If you put in a number for x, you're only going to get one number for y. All right? So go ahead and see if you can figure out the function rule for this, the amount of water used. All right, I hope you remembered the form, the simplest form of a linear equation, which is the slope-intercept. And you can find the slope by looking at the pattern. It's going down 12 for every 1 minute. The rate is also the slope that goes in front of the x. And then whatever you're starting with, the 0 value, gets added on. So that looks like that. Okay. Now, if you make a graph, you can tell if it's linear if you see one of these three things, some kind of a straight line. Okay. If it's a nonlinear function, then you're not going to get a perfectly straight line. You're going to get some curvy line or maybe even random dots. All right, so go ahead and graph these as best you can and then decide if this is linear or nonlinear. If they all line up, you're going to call it linear. If they don't line up, you're going to call it nonlinear. I think these are all going to line up, and in fact, I'm going to, I think this is a direct variation graph. So, and I think it represents a number of centimeters per inch. Okay, so so from this table here, you can see some ordered pairs. 1 goes with 1/2, 2 goes with 1/4, 3 goes with 1/8, 4 goes with 1/16. Now go ahead and graph those on there and decide if it's linear or not. I don't know if you can see it, but it kind of looks to me like it's starting to curve. So we're going to say this one's nonlinear. All right, once you know it's linear or nonlinear, then that can help you write a rule. You're familiar with linear rules. We're going to do a couple here that are nonlinear, but again, you might be able to tell what's going on by looking at the numbers. If you look closely at this one, and then this will be a hint on how you're going to do the next one on your own. But the relationship here is when x is 1, y is 1. When x is 2, y is 8. It's really going up by a lot, 27, which kind of is leading me to believe there's something with multiplying here or exponents. And if you think about this, this 8 is actually 2 times 2 times 2. This 27 is 3 times 3 times 3, 4 times 4 times 4, 5 times 5 times 5. The next one is going to be 6 times 6 times 6, which is 216. So the rule is you take x and do it to the 3rd power. We call that the cubic function. Go ahead and look at the second problem here, problem 3. Fill in the table, see if you don't see a pattern, and see if you can write the function rule for that, or the equation. So y equals something. All right, and I hope you noticed that the output is actually the input squared, or multiplied by itself, and that equation would look like this. All right, so when trying to find a rule, you kind of have to make sure it works for all the points. If you look closely here, you might think that this is linear and it's going up by 1, at least for the first 2. So your classmate thinks that y equals 1x plus 1 would work. The problem is it doesn't work for this one. Y equals, if x is 2, y would equal 2 plus 1, which is 3, not 5 like this one. Okay, so you have to look a little deeper sometimes to see what's going on. Personally, I'm seeing some more multiplication in there. I'm seeing that from the last problem. Remember, 4 times 4 is 16. 3 times 3 is 9, 2 times 2 is 4, that it's always one more than those numbers, which this one will work for all of those. All right, to graph a rule, just make a table, and you don't need a lot of values. This, the inputs are along the x-axis, so this has inputs like -4, -3, -2. I'm not going to do all of those. I'll just do from -3 to 3. And then we have to square that. Remember, when you square a negative, you get a positive. So -3 times -3 is 9, minus 1 is 8. -2 times -2 is 4, minus 1 is 3. 1 minus 1 is 0. 0 minus 1 is -1. 1 minus 1 is 0. 4 minus 1 is 3. And 3 times 3 is 9, minus 1 is 8. So -3, 8. -2, 3. -1, 0. 0, -1. 1, 0. 2, 3. And 3, 8. And we can see that we got some kind of a curvy thing going here. All right, and that's a nonlinear graph. Go ahead, you try one. All right, so to graph these, just find some, pick some x values and then find what the output would be for those. All right, I'm going to stop here. We'll cover this function notation tomorrow, but you should be able to do the problems on your homework at this point. Let me know if you have any questions. I'll see you soon.